First of all, it's a pleasure to talk to you and to have the chance to give this brief report about cosmic rays around the knee. And I want to thank Leonid and all the organizers for giving me this opportunity. Before I go into the details of this presentation, let me make one remark. This is my first conference since 2019. During all the pandemic, I had no chance to attend or to follow any conference. So I'm updated. I know the new results only by online material, slides that I can find from websites and articles that that have been published recently. So I'm sure that this makes my review incomplete and not surely not updated with the latest results. It's clear that the information we get, meeting people, speaking with people, following conferences is much more useful and better than what we get through the web. So I apologize since the beginning that my review will be surely incomplete and some new results may lose because I'm not aware of them. I'm sorry. So speaking about cosmic rays around the knee means speaking about the three main tasks and measurements we have on the subject. So the all particle spectrum, what now we can call the masses group spectrum, that was previously called the cosmic ray chemical composition, and the search for large scale anisotropy, and in general the search for anisotropy that's giving new interesting results in the recently. So discussing the cosmic rays around the knee, we cannot limit ourselves to indirect measurements. So what we can perform on the ground with extensive air showers experiments. But we must also consider the data we obtain from direct experiments, like those that are running and operating on satellite or on the International Space Station. These experiments are approaching the knee energies, and we have an overlap between direct experiments from satellites and indirect experiments, mainly those that are operating at a high altitude. I will come back to this point very soon. So to summarize, let me summarize very briefly and shortly what are the pros and cons of the two techniques. With direct measurements, it's clear that we have a very good resolution on the charge of the primary cosmic rays, and so we can resolve elements one by one, and we can attribute each single event to a precise primary particle. So we can identify the primary particle that originated the event. We have a good energy resolution. All these experiments operate calorimeter and can directly measure the energy of the event. Even if these experiments are limited by the mass of this calorimeter that limit the energy range that can be precisely measured by these experiments. Approaching higher and higher energies, these experiments, even the direct experiments, have to face the problem of the absolute energy scale calibration. I mean, a direct experiment can be easily calibrated. We can make a absolute energy calibration using a test beam and exposing our detector at a test beam. But this moving to higher and higher energies becomes more and more difficult, and we have no accelerator operating at very high energy. So when we extrapolate the measure, when we reach higher and higher energies, we can arrive at 100 TeV with direct experiments. We have a problem of energy scale calibration, absolute energy scale calibration, even with direct experiments. So we must always remember that even with direct experiments, there is a limit in the energy resolution due to the mass of the calorimeters and due to the energy we can contain inside this calorimeter. And there is a problem of the energy scale calibration. The sure, big, enormous advantage of direct measurements is the fact that we can attribute every single event to a precise primary particle. We can identify the primary particle for each single event. Then we must always remember that we have a problem with statistics. Satellite and even ISS experiments are limited by surface, so we cannot hope to have a huge statistics at a very high energy. On the opposite, extensive shower measurements, so experiments running on the Earth surface, have no statistical problems. We can make these experiments big, large. It's only a problem of manpower and fundings. It's not a problem of logistics. We have, for sure, we will never have the possibility to have to identify the primary particle for each single event. This is already prevented from shower development fluctuation. Even before we measure the extensive air shower, the shower fluctuations prevent the possibility to classify each single event and to assign each single event to a precise primary particle. The energy calibration of these experiments is a major task. It's the biggest problem of these experiments. Only with fluorescence light technique, we can have an almost direct measurement of the primary particle energy. And we know that this technique is difficult to operate at the energies of the knee. The fluorescence light signals is very small, and it works well only at very high, at ultra high energies, above 10 to the 18 electron volt, order of magnitude. And so we must rely on the extensive air shower simulation. And this introduces a systematic error and a problem, a difficulty, not a problem, a difficulty in the absolute calibration of the energy scale of this experiment. We must have well under control the systematic errors of these experiments. This is one of the main difficulties we have in running these experiments, to control and to cope with systematic errors. Having all this in mind, a least this is my opinion about these measurements. Let me go to a partial and brief summary of the latest results with the warning I've said before. Let me start from primary measure, from direct measurements. And speaking of direct measurement, we can have a look at the spectra of the single elements. In this plot, I've taken the hydrogen, the proton spectrum, published, I think, from the Calette collaboration last year, 1 year ago. And in this plot are also reported some of the latest measurements like IMS, CRIM, or DAMPI. I'm sure this is partial and incomplete, but it's just to give an idea, to have an idea of what are the latest measures. As we can see from this plot, the data points agree inside the systematic error that are shown by the gray band in the plot. the points of the single experiments are differs from one another on the absolute scale, but the differences are inside the systematic error. Where we have an agreement, a general agreement, is in the shape of the spectrum that has been measured. And we can clearly see that in the energy range from 10 GeV to 100 TeV, more or less, the proton spectrum cannot be described by a single slope power law. We have two change of slope in this spectrum. One is around 200 GeV, where we have an hardening, and another one is around the TeV energies, where we have a softening. And more or less all the experiments agree on this structure of the spectrum. And also other results, like those from ETIC, nucleon, that are not reported in this plot, agree with this spectral measurement. Moving to helium, we can here in this plot is shown the helium spectrum. Please notice that in the helium spectrum is multiplied to the energy to the point 2.6, while the hydrogen spectrum were multiplied by the energy to the 2.7. So the Y scale of this plot is different. In the helium spectrum, we can see more or less the same features we have seen in the proton spectrum, a hardening at 200 GeV per nucleon, and a softening at TeV per nucleon. The energy scale of this plot is in energy per nucleon. Again, the differences in the absolute scale are smaller than for hydrogen, but the data are not completely overlapping one to the other. There is a small difference that is due to the energy calibration. The agreement is inside the systematic error, but this shows us what I was saying at the beginning. We must take care of the absolute energy scale calibration. That is one of the main difficulties we have in running and operating this experiment. And this is clearly visible by all these results. Moving to heavier elements, in this plot are shown the carbon and oxygen spectrum, so elements of the CNO group. And again, we can see the hardening at hundreds of GeV per nucleon here, around here. Again, we can see the differences in the absolute scale calibration that is reflected in differences on the y-axis on this plot, because we multiply the flux to the energy to the 2.7. A better agreement is obtained when we compare the ratio between carbon and oxygen. This again accounting for the fact that all experiments agree on the spectral shapes, and that the differences between all these data are only due to the calibration of the energy scale. Moving to heavier elements, sorry, in this plot are shown the iron spectrum measurements. Again, you can see the band, the typical band of the systematic errors, and we have the similar consideration that were already done for all other elements. We have an agreement of the shape. There is a hardening around 100 GeV per nucleon, and there is a general problem of normalization of this spectra. Leaving the measurements we can obtain from direct experiments, we can go in the energy range where we have an overlap between direct and indirect cosmic ray measurements. So where we have an overlap between the satellite and the ISS experiments and those measuring extensive air shower from the ground. And this overlap is mainly due to high altitude experiments that can measure showers near the maximum development and can reach lower and lower energy threshold, study of the cosmic ray spectrum. In between these experiments, we must remember the Argo YBJ experiment that ended its operation a few years ago. And nowadays we have the Oak, the Tibet, and the LASO experiments running, and the others that I surely forgot. One very important point of all these experiments that operates near the shower maximum is that the number of electrons at shower maximum, as we well know, weakly depends on the charge of the primary particle. So we have a weakly dependence of the number of electrons at the shower maximum on the chemical composition, on the nature, on the type of the cosmic rays that has originated the shower. These experiments usually have a very high fill factor. So the ratio between the active surface and the total surface covered by the array is very high. Oak reaches 60% fill factor. Argo was more than 90% fill factor. So these experiments have a very precise measurement of the extensive air shower geometry. They can have a very precise determination of the core position and of the arrival direction of the shower. And another advantage of these high altitude experiments operating at low energies is that they can measure the shift of the moon shadow with respect to the position, to the actual position of the moon, And this gives them the chance to check the absolute energy calibration. You can use the geomagnetic field to as a spectrometer and have an absolute energy calibration. In this plot, I show the energy resolution and the energy bias of the oak experiment. We can see that on the measurement of the energy bias, the error bars are still large. So it's true that we have a check and a control of the energy scale, but the precision with which we can control this energy scale is still limited. It's much better than what we do with higher energy experiments, but we still have a problem of energy scale calibration. And the energy resolution that can be achieved with oak is from 25% to something around 10%. The oak collaboration showed, published the all-particle spectrum in a paper in 2017, and at the last ICRC in 2021, published a new set of data extending the energy range. We have 3 more points with respect to their results in 2017. And this new measurement essentially confirms the old one, and the differences are well within the systematic error. We can see that at the low energies, we have a good agreement with the nucleon and the attic data of the all-particle spectrum, and at the high energies, there is a good agreement with the taiga, high score, tunga measurements. While the measurements of the oak are a little bit above those of Argo, YBJ, of Tibet, and of the iStop collaboration. The spectrum measured by oak from hundreds TeV to 10 PeV is not described by a single slope power law. They observe a knee feature, and this knee feature is around 50 TeV. In their paper in 2017, the energy of this break was 45 TeV, while at the ICRC they claimed that the energy break is at 70 TeV, even if with a larger error. So no matter exactly where this break is located, but from the oak collaboration, we have the indication of a break in the power law spectrum, change of slope from 2.5 to 2.7, around 50, 60 TeV, okay? Even from this measurement at low energies with high altitude experiment that has the chance to use the moon shadow displacement to check the energy scale, there is a energy scale calibration task. And this is shown by the differences by the oak and by the Argo data points in this plot. The Argo data points seem to agree better with the CRIM measurements. Our oak data are a little bit higher, but as we have seen before, if if we take the nucleon and ethic data, then we have that the Oak data agrees with this experiment, and the Argo are a little bit lower. So we don't know the exact energy scale, but we must always remember that no matter which technique we use to measure the cosmic rays, we must be very, very careful on the energy scale absolute calibration, both from direct measurement and from high altitude experiments, and more and more important when we go to higher energies experiments like those studying the knee. Okay. No, sorry, went back. Moving to higher energies, we move to experiments that not necessarily operate at high altitude. We have the iStop experiment operating at the South Pole, that is at 2,800 meters above sea level. But Cascade and Cascade Grande were operating at sea level. Tunca is 600 meters, if I'm not wrong. So these experiments operate well below the shower maximum. So they observe showers in the absorbing phase. This is less important for Tunca, that operates with Cherenkov light and has a quasi-calorimetric measurement of the primary energies. We have no possibility to check the absolute energy scale of this experiment. We must rely on shower simulation with computing code like Corsica. Essentially, we use Corsica as a reference for the simulation of extensive shower. The only result which allowed energy scale comparison between two different extensive shower experiments is the one that was obtained with the radio measurements of Tunca Rex and Lopez, that can be used as a common energy scale to compare the Tunca and Cascade Grande measurements. And the authors have obtained that the two energy scales show a systematic difference that is smaller than 10%. What we know about the spectrum, the all-particle spectrum above the knee, is that this spectrum cannot be described by a single slope power law. In this table, I summarize the results obtained by different experiments about the slope of the spectrum above the knee, above the hardening, and above the second knee, or the steepening that we observe at 100 PeV, and the energy scale at which these features are observed. In this slide, I show three of these experimental results, clearly showing all of them cannot be described by a single slope power law. In this complicated plot, I've reported all the many, not all, many measurements of the all-particle spectrum obtained by different experiments, and mainly for the Cascade Grande experiment, to which I participated and I have easier access to the data. I've reported the spectrum calibrated with 5 different hadronic interaction modes. And we can see that there is a spread of the measurements of every single experiment due to the hadronic interaction model we use for the energy scale calibration. And with the error bars I've reported on the plot, I showed the effect of a 10% error on the energy scale in this y-axis where the energy is multiplied to e to the cube. The blue bar is the 20% error bar, and the green bar is a 30% error on the energy calibration. So we can see that essentially this data agrees inside this systematic error, and that if we consider the data points from different experiments calibrated with the same hadronic interaction model, the differences are much, much smaller. And these are the points of the same color, but with different markers. The same color indicates the same hadronic interaction model used for the energy calibration. So essentially, we can say that like we said for the direct measurement, the differences between the experimental data we have on the all-particle energy spectrum are due to the energy calibration of these experiments. The spectral features that are observed by different experiments agrees. We don't know exactly the energy at which this feature appear because we have this problem of the energy scale calibration. Let me summarize these all these remarks about the all-particle spectrum. What we surely know is that the cosmic ray spectrum is much more structured than what we thought in the past. It's not true that the cosmic ray spectrum is a power law spectrum with only the break at the knee. We have much more structure than this. As I've stressed even too much in my presentation, the main problem, I think, is the absolute energy calibration. We must have well under control the role of the extensive air shower simulation. The biggest uncertainty in the extensive air shower simulation is the hadronic interaction model. And here we can we can hope to have good news from the LHC experiment. But what we know is that we have a good agreement that all experiments agree on the observed spectral features. Now we can move to what was called the chemical composition studies, and what I now prefer to call the mass group spectra. With the increasing resolution of extensive air shower experiments, we can now measure and study directly the spectra and the characteristics of different mass groups of elements. The mass group separation can be done with two different approaches. Either we try to classify each event, attributing this event to a specific mass group, or we can use a statistical approach where we interpret the observable of the shower we measure using a statistical approach. In the event-by-event approach, we can use the most diffuse technique is to use the muon and electron number at observation level. For instance, the Cascade and Cascade Grande collaboration used the ratio between the muon and the electron number reported with the constant intensity cut technique at a reference angle. or we can use the shower morphology, that like the shower age, the slope of the lateral distribution, or the Ayers-Cherenkov light image. This technique were those used by the Argo experiment. With this technique, up to now, we are able to separate two mass groups, the light and the heavy primaries. In the near future, I'm optimistic and I think we can separate at least 3 mass groups, but maybe also 4. I don't know. With this approach, the dependence on the extensive shower simulation is not so huge. There is a dependence, but not so huge. Separating the events into mass groups using an event-by-event approach allows not only the measurement of the energy of the spectrum of each mass group, but will in the future also allow the measurement of the large-scale anisotropy for each mass group. With the statistical approach, is the one that was introduced by the Cascade collaboration. For instance, we measure the two-dimensional spectrum of the number of events falling in a pixel with a certain muon number and a certain electron number. And we can reproduce this observable like with the contribution of different elemental spectra that is the quantity that we want to measure, multiplied by the probability that an event originated by a primary particle with mass number A and energy E originates a shower that is classified with a certain muon and electron number. And this probability can only be calculated with extensive shower simulation. And this term is what introduces in this technique a huge and strong dependence from the extensive shower simulation of this approach. Another approach is the one used by the Oak collaboration, which makes a plot of the shower age versus the primary energy of the primary particle. This is N is the number of events observed in a bin of shower age and energy, primary energy. And this can be obtained as a sum of many contributions. Again, we have the phi, that is the spectrum of each element, and the probability that an event of a certain primary particle with a certain energy originates a shower that is classified in a particular pixel of this bidimensional spectrum. Again, this probability can only be calculated with extensive shower simulation. With this technique, experiments have been able to separate up to 5 primaries, usually hydrogen, helium, the CNO group, an element that is representative of the elements just below the iron, and the iron as the heaviest primary particles we have in cosmic spectrum. As I said before, there is a heavy dependence on the extensive shower simulation. With this approach, only the spectrum of each mass group can be measured. We cannot obtain any information on the large scale anisotropy. So with this statistical approach, we can try to have the information of more mass groups, but we pay this with using an analysis technique that has a heavy dependence on the Earth's extensive shower simulation, and we lose the possibility of measuring the anisotropy for each mass group. What are the results that have been obtained? The Oak collaboration presented the results separating three mass groups: hydrogen, helium, and all the elements heavier than helium, what they call heavy. The spectra they have obtained are shown in this figure with their corresponding error band. We can clearly see that all these spectra are better described by a power law with changing index. They are not the best chi-square is surely not obtained by a single slope power law, but it's also true that a single slope power law is in any case inside the systematic error band. So we can say that with the actual Hawke measurements, spectra with not described by a single slope power law are favored, but the single slope power law are not excluded within the systematic errors. Okay. If we trust these measurements, we have a softening of the spectrum around tenths of TeV, and we have a hardening of the helium and the hydrogen spectra around 100 TeV. But we must be very, very careful in claiming these structures, because we can immediately see from these error bands that the systematic error is much bigger than these structures. So I would be very, very careful in claiming all of these structures in this spectrum. The same data points have been compared by the Hawke collaboration with the results of direct measurements. And we can see that hydrogen and helium are in agreement with JC, ETIC, Dampe, and CREAM experiments. And the nucleon data are in agreement with the helium spectrum and are a little bit above the hydrogen spectrum, but at the limit of the systematic errors. Concerning the heavy mass groups, all elements heavier than iron, the Hawke measurements are a little bit above all other reported data. Again, we must be very careful and in not claiming too much as far as we have all this systematic error in the energy calibration. Other data with a statistical approach have been published by the iStop IceCube collaboration in 2019. In this data, the measurement of the electromagnetic component of extensive shower obtained with the surface iStop experiment are compared and correlated with the number of muons measured by the IceCube deep under ice detector. With this approach, this collaboration separated 4 elements: helium, hydrogen, oxygen as a representative of the CNO group, and iron. The data obtained by the iStop IceCube collaboration agree with the model of Professor Geiser that are known like H3A and H4A. So we have a general agreement with this model that are based on knee-like feature with the energy of the knee depending on the charge of the primary part. The iron flux expected in this measurement is higher than those obtained by other measurements. Let me quickly remind these old data. These are 20 years old now data from the Cascade experiment, just because Cascade is the collaboration that introduced this analysis, this kind of analysis. With these two plots, we can immediately see how the relative fraction of events of the different primary heavily depends on the interaction model we use in the simulation. If we analyze the data with Sibyl, the spectrum is dominated by carbon, while if we use QGS-Jet, the spectrum is dominated by helium. The common feature between the results obtained with different interaction model is that the spectra of the light elements always show the knee, and that the knee, the position of the energy of the knee increases with the mass of the primary part. No knee of the iron component was observed by Cascade. This is a summary of some of the results obtained by a statistical approach to mass group separation. Now let me go to an event-by-event classification. On the left plot is the spectrum obtained by Argo, where they have used the extensive Earth shower image measured with the telescope they were testing for the LASO experiment. While on the right of the plot is the muon number spectrum, the density of the muon density spectrum measured by Cascade. In the case of Cascade, the spectrum of the electron-rich and the electron-poor extensive Earth shower samples, that means electron-rich means the light elements, and electron-poor means the heavy elements, are shown. And clearly from this plot, we can see that the knee is observed only for the electron-rich group. An energy is not calibrated in energy, this figure, but we can use the integral flux above the change of slope to have an idea of the energy of this change of slope. And this energy corresponds to the energy of the knee. While Argo claims a sharp break in the primary proton spectrum around 700 TeV, so at an energy below TeV. So these two measurements are somehow not coherent with each other. The two energies, both of them observe a change of slope of the light mass of the light elements, but at different energies. The energies are not compatible inside the systematic errors. The event-by-event classification technique was also used by Cascade Grande, moving to higher energies. And here we can see that we have no change of slope of the light elements, and we have a change of slope of the heavy elements, always using this electron-poor and electric-rich sample, not to claim, because experimentally what we do is we separate the events between electron-rich and electron-poor. Then we know that this can correspond to light and heavy elements. But experimentally what we do is separate the two samples, electron-rich and electron-poor. In this was the first observation of the knee of the heavy elements that is observed around 10 to the 17 electron volt, where at the same energy where the Cascade experiment observed what we can call the second knee. Observe a softening of the spectrum. With Cascade Grande, we have also studied more in details the spectrum of the light elements, and we have observed this hardening at an energies greater than 10 to the 17, and that is not the same energy where we have observed the knee of the heavy elements. So the knee of the heavy elements and the hardening of the light elements observed by Cascade Grande are two different spectral features. Concluding this discussion of the mass group spectra, we can say that the actual experimental resolution allow us to study the chemical composition using more details of the two-parameter distribution that we have always used for this scope. I mean, we are not limited in using the mean value of the muon or electron number, but we can use the complete distribution, the mean value, the width, the shape of this distribution. We can analyze in much more details the data we obtain. We are able to separate 2 to 5 mass groups, 2 mass groups using an event-by-event technique, and up to 5 using a statistical approach. I have a preference for the event-by-event technique because the dependence on the extensive shower simulation is smaller and allow us to measure also the anisotropy of different mass groups. We had important information from these studies, but we must always keep in mind that there are discrepancies between the measurements at high and at low altitudes. And we don't know if we are observing different spectral features. If we introduce something due to a not completely correct knowledge of the extensive shower evolution in atmosphere, we don't know. We don't have a final answer to these discrepancies that have been observed. I think that the best we can do is wait for new data. LASO experiment, this very big, huge experimental facility operating in China since 2 years, will surely give high resolution, high statistics information, and may help us in solving these these discrepancies. Concluding, I want to discuss the anisotropy. The resolution we can obtain on the anisotropy measurements depends essentially on the number of events we have on our sample. So huge statistic is necessary, and therefore very large area experiments are required to extend these measurements to higher and higher energies. The high energy measurement of the anisotropy we have is from the
Andrea, sorry, how many minutes you need else?
Sorry?
How many minutes are you required?
5 minutes is okay, 5 minutes.
Okay, okay.
Okay, okay. So we must have large experiments. These experiments must be very stable and must have a very good control of the counting rate variation. Differently from what I've discussed from all particle and mass group spectra, here is important to have a complete sky coverage and to have experiments both in the northern and in the southern hemisphere. And at the moment, we don't have any measurement of the large scale anisotropy for different mass groups. The technique with which we measure this anisotropy is making the distribution of the counting rates in beams of sidereal times. For instance, this plot is taken from the Cascade Grande anisotropy studies, and we fit this distribution with with a dipole, and we obtained the amplitude and the phase of this dipole. In this plot, I summarized the results on the dipole amplitude. The highest energy data point we have is this one from I stop. Then we have only upper limits from Cascade Grande. And at ultra high energies, we have this very important point from the Auger experiment. Together with the amplitude of the dipole, we can measure the phase of the dipole. And what is interesting is that we have a flip of the phase above 10 to 14 electron volts. So approaching the D energy, the phase of the harmonic changes in the direction of the galactic plane. While at the Auger energies, again, we have a change in the phase of the anisotropy. So this is an indication that we have something interesting happening at the energy of the knee. And we need more and more data at these energies. The only study covering the complete sky is this one made by the Oak and Ice Cube collaboration together, and that is represented in this plot. We have a general agreement, a good agreement of the measurement obtained by the both experiments. And the combined observation can eliminate biases due to the limited field of view of individual experiments. Subtracting the large scale anisotropy, the Oak and Ice Cube at 10 TeV can enhance some small scale anisotropy, like this excess coming from region A, region B, what they have called region A and region B. So this was just to say that we can go deep in the study of the anisotropy and not only limit ourselves to large scale anisotropy. To conclude, let me conclude. I don't have a real conclusion. I just want to make some remarks that are essentially those that I already did. What is important and what is, in my opinion, sure, is that the cosmic ray spectrum is much more structured than what we know we thought before. This last generation experiment. We have a general agreement about the spectral shapes. The main differences between measurements are due to the energy calibration. And I stress again that this point is the main point to understand all these results. Studying the mass group spectra, the knee of light elements is observed at lower energy than the one of the heavy ones. We have differences between measurements obtained at high and low altitudes, and we will wait for new results like those coming from LASO. With measurement of the large scale anisotropy, we have almost reached the knee energies. To reach higher energies, we need only larger experiments. And what will come in the near future from LASO and from other experiments is a study of the anisotropies for different mass groups. And this will be a new and interesting information about cosmic rays around. It's important to remember that it's mandatory to have a complete sky coverage. So if we have a LASO in the northern hemisphere, we have a lack of experiments in the southern hemisphere. In this report, I've not discussed what's called muon puzzle, but we must remember that all these data rely on the shower simulation that is far from being accurate and complete. We know that there is this muon problem, the muon number problem, and it's important that with extensive shower experiments, we continue to study the features correlated to the hadronic interaction models, because with extensive shower experiments, we cover energy range larger than those that are covered by collider experiments, and therefore we can only trust on extensive shower experiments to extend our knowledge about hadronic interaction. Thank you very much and for your attention, and